This is the lecture for Module 3 of Unit 1 concerning more information on phase transitions. Let's take a moment to review what we already know. According to the Clausius-Clapeyron equation, at a given pressure, liquid-to-gas transition occurs at a certain temperature. Here we have one form of the Clapeyron equation again. Remember, when you worked examples or worked problems with equations, that the pressure P2 matches to a distinct temperature T2, and the pressure P1 matches to a distinct temperature T1. The temperature for a given pressure is the temperature at which the liquid turns to the gas. So at any given pressure, liquid-gas transitions occur at a constant temperature. Now, one effect of this is what this means is the temperature does not change when the gas is vaporizing. One way of representing this sort of information, the fact that phase transitions occur at a constant temperature, is with a heating curve for a substance. This diagram is a heating curve for water. Now, just as liquid to gas transitions occur at a constant temperature, solid to liquid transitions occur at a constant temperature, at least for a given pressure. Now, as you will see, the heating curve for water shown here corresponds to a pressure of 1 atmosphere. Now, on the x-axis of this diagram, you see increasing heat. Imagine heating a sample of water, and as we do that, time increases as well. Alright, so at the beginning of this process, our sample of water is at negative 20 degrees in this diagram. At this point, the sample of water is all solid, it's all ice, and as we add heat, we see the temperature of the material increase as it is warmed up. This will occur until the temperature reaches 0 degrees. At this point, when the temperature reaches 0 degrees, the transition to water begins. And we will add heat at the constant temperature of 0 Celsius until this transition is complete. You notice we are now, as time goes on, the temperature on the y-axis is not increasing. If our sample is a mole of water, then the amount of heat that has to be added in this flat spot is equal to the molar heat of fusion, or the heat of melting the material at 0 degrees. For water, that's around 6 kilojoules per mole. At this point in the diagram, all of the solid water has been converted to liquid. And as we add heat, the temperature begins increasing again. Now you can heat our hypothetical mole of water, or whatever size of sample of water we like, until the temperature reaches 100 degrees at 1 atmosphere. Now you will remember that 100 degrees is the boiling point of water, or the temperature at which the pressure is 1 atmosphere. At this temperature, the normal boiling point, heat is added to liquid water to convert it to vapor. Notice the temperature of our sample, again, does not increase at this point. The phase transition occurs at a constant temperature of 100 degrees. In this case, the amount of energy that will be added if our sample of water is 1 mole, the amount of energy added will be equal to the molar heat of vaporization for water, which is about 41. At this point, after all the liquid has been converted to gas, the temperature of the gaseous water increases as heat is added. Essentially, a curve like this can be produced for any substance, in principle, not just water. This diagram will show the freezing or melting temperature and the boiling temperature. Now you can imagine a cooling curve. Naturally, this shows the same features as a heating curve. Here we have, again, temperature on the x-axis and time, but heat is leaving, not being added to the system in this case. Our starting point is 200 Celsius in this case. And if we begin cooling steam, gaseous water, as we take heat out, the temperature goes down until 100 degrees is reached, at which point condensation begins. The transition from gas to liquid then occurs at a constant temperature of 100 Celsius as heat is removed from the sample. At this point, all the gas has been converted to liquid, and as further heat removes, the liquid is cooled. This diagram shows a phenomenon which does not always occur. Typically, the liquid is cooled to 0 Celsius, and then freezing begins, and energy is extracted until you reach this point. Point F is the point at which all the liquid has become a solid. Then further cooling drops the temperature of the solid ice. This abnormal point shows a supercooling of liquid water, which can happen in some circumstances in which water is cooled rapidly. In this case, the liquid dips below the freezing point of water. This is a metastable state. And when it does exist, which is not frequently, the system will revert to point E as cooling continues and ultimately arrive at the same point. A sample which is entirely solid is formed at 0 Celsius. Okay, so cooling is typically the reverse of heating. In most circumstances, you cool to a temperature of 0 Celsius and then freezing begins. But there are some unusual situations in which water can be supercooled to a few degrees. However, additional cooling causes it to revert back to a normal mixture of liquid and solid and then form ice as cooling continues. Again, the take-home lesson for this curve and a heating curve is that phase transitions, gas to liquid and liquid to solid, in normal, stable situations, occur at one temperature. Another way of representing this sort of information is a phase diagram. Here we see a phase diagram for carbon dioxide. Carbon dioxide is a gas under normal circumstances. However, let's consider abnormal circumstances. For example, on Venus, the pressure of carbon dioxide is, well, let's say something close to 80 atmospheres. Now, at 80 atmospheres, what this diagram shows, notice pressure is on the y-axis. Carbon dioxide is a solid to temperatures as low as negative 100 Celsius, down here on the x-axis. And the solid can be heated to roughly negative, well, a bit over negative 60, it looks like, this point. And at this point, the transition from solid to liquid begins. Again, what we see is at this temperature and pressure, I have marked here, solid and liquid exist at the same time and are in equilibrium with each other. You could have heating or cooling. One could be putting heat in or taking it out, going backward and forward. The phase transition occurs at one temperature. When it is complete, liquid carbon dioxide exists and may be heated, heat added, until temperatures of around 30 Celsius. Now this is above what is called the critical point on a phase diagram. At this point, the densities of liquid and gas are equal and the two become indistinguishable. So somewhere at temperatures in excess, of, it looks like around 30, we enter the region in which liquid is indistinguishable from gas. If we consider a pressure of 40 atmospheres, notice that the solid to liquid transition occurs at a somewhat lower temperature. In other words, reducing the pressure on carbon dioxide by about 20 atmospheres reduces the melting point a few degrees to a lower temperature. After the transition from solid to liquid is complete, the liquid can be heated to, it looks like, maybe this is about 5 degrees Celsius. At this point, around 5 degrees Celsius at a pressure of 40 atmospheres, boiling occurs. Liquid and gas exist together at the same temperature. Again, they're in equilibrium. The process may be going either way, as long as the process will. Both can exist as long as at this pressure and temperature. If heat is added, complete vaporization or boiling will occur. And you will then have gaseous carbon dioxide. As you heat the gas, the substance, the temperature of the gas increases. Alright, so in effect on the phase diagram, there are areas, you see, which show areas or pressures and temperatures at which solid exists, or liquid exists, or which gas exists. And then there are intersections like this. These correspond to pressures and temperatures at which melting or freezing occurs, depending on which way you're going. In other words, this is the line in which solid and liquid can exist at the same time. These pressures and temperatures, solid and liquid, can be in equilibrium. Likewise, on this curve, we see pressures and temperatures at which boiling or condensing occurs when liquid and gas can be at equilibrium. So the lines, solid, liquid, and liquid gas, represent, well, in one case they represent melting or freezing temperatures. In this case, condensing or boiling temperatures. Here, liquid and gas at these pressures and temperatures can be at equilibrium. This line describes the temperatures at which solid and liquid can be at equilibrium. One more interesting feature on the diagram is the triple point, the temperature and pressure at which solid and liquid and gas can exist at the same time. In general, a substance will have one triple point. There is one pressure, one temperature, in which all three substances can exist in equilibrium at the same time. Notice the triple point of carbon dioxide is still at very high pressures, around 5 atmospheres. Here we have a curve below the triple point. This curve represents pressures at temperatures at which solid can transform to gas. Okay, this process is known as sublimation. And notice that at a pressure of around 1 atmosphere, it occurs around negative 70 Celsius. In fact, it's possible to buy solid carbon dioxide, quote-unquote dry ice, at temperatures that are lower. And when the substance heats up to negative 70, it begins transforming to a gas. Again, and can transform from solid to gas at that temperature as the substance absorbs heat. So if you buy dry ice, you are buying a solid, and it begins sublimating or evaporating into a gas on this solid gas line, pressures and temperatures at which solid and gas can exist at the same time. Another feature is to note, well, we have noted that the melting point decreases as pressure decreases, or the melting point increases as pressure increases. In carbon dioxide, solid is more dense than the liquid. It is possible to start with a certain substance at a certain pressure, 20 degrees, say at 20 atmospheres, and this is quite cold, negative 50-something degrees. And you can imagine heating, or rather increasing the pressure on the substance that looks like at around 80 atmospheres that are higher, and transform the liquid to a solid. As the solid is more dense than the liquid, increasing the pressure on the substance results in solidification. Pressure increase causes the substance to form the more dense phase, the solid phase. And so again, the solid liquid line shows that you can freeze the liquid in some circumstances by increasing the pressure. Here we see phase diagrams for water. In particular, here in the left-hand side, we have a phase diagram for water. And we see that 1 atmosphere's pressure is quite low down here. On the solid liquid transition at 1 atmosphere occurs at 0 Celsius, and the liquid vapor transition occurs at 100 Celsius. In other words, here is the liquid gas line, and normal boiling temperature of 1 atmosphere is way down here. Liquid gas line always shows an increase in pressure as temperature increases. Notice that we can cause condensation at quite high temperatures, 300 Celsius, if we simply increase the pressure until it reaches 100 atmospheres. Let's consider a pressure around 100 or around 100 atmospheres or above. The melting point doesn't change much, but you'll notice it's gone down as pressure has increased. Meanwhile, the boiling temperature at which liquid and gases can exist in equilibrium have, of course, increased as we've increased the pressure to above 100 atmospheres. In other words, the solid-liquid line on the phase diagram of water has a negative slope. Melting point goes down as pressure goes up. See, it's possible to start out with a solid down here at pressures of 100 atmospheres at 0 Celsius, and by increasing the pressure to 400 atmospheres, the substance can be forced to transition into the liquid phase. So unlike carbon dioxide, because an increase of pressure causes melting, and this happens because the solid is less dense than the liquid. Now, the slope of this line is different in this diagram compared to the diagram for carbon dioxide we have just seen. The diagram for carbon dioxide exhibits a positive slope, whereas this slope is negative in the case of water. However, there are points that do occur on all phase diagrams. Water has a triple point, for example, at pressures somewhat below 1 atmosphere. Remember that at this point, solid, liquid, and gas can exist at the same time. And there is a critical point at which liquid and gaseous water can no longer be distinguished from one another. Their densities are the same. This typically occurs at extremely high pressures, and notice in this case at very high temperatures. The right-hand side of this diagram shows a close-up of the liquid-solid line for water, emphasizing the fact that the slope is negative. In other words, I can start with a sample of ice here at a temperature of -1 Celsius and 1 atmosphere, and melt it at a temperature of -1 Celsius and a pressure of 150 atmospheres. In fact, it looks like the transition from liquid to solid as the pressure increases at this point occurs somewhere around 125 atmospheres. So again, increasing the pressure of water causes melting, as shown in these phase diagrams. This concludes this lecture on diagrams and their illustrations of phase transitions.